So here's our good old trough problem. This is another classic problem. It's pretty neat the way it works out. A trough is 22 feet long, 14 feet across at the top. It ends our isosceles triangles with a height of 6 feet. Water runs in the trough at the rate of 3 cubic feet per minute. Okay. How fast is the water level rising when it is 5 feet deep? So I kind of used almost the same numbers I used for the cone. Okay, so let's take a look, and I'll do a sketch over here. And this is my trough. Now it's basically like a triangular prism. These are the bases and this is the height. So we know the volume of a prism is just base area times height. In this case it's going to be a triangle. And the height, we'll call this the length rather than the height because we're going to be using height for the triangle. So we'll call this L. And let's see what we've got here. It says water is going into it. So we've got 3 meters cubed. Yep, 3. Oh, this is cubic feet. The other one was meters. This is feet cubed per minute. I guess it's minute. Yes, it's minute. So that would be my dVdt. This is volume, so it's going to be per minute, so it's rate of change. So dVdt equals 3. And we're going to be dealing in cubic feet now. Okay, and we want to know how fast the water level is rising. So this is going to be the height of this, and you can just visualize it. You're pouring water in this trough, so there's a little line over here, and that's the height at any time. I guess you could draw this line parallel here like this, so you can kind of see what's going on. If you could see the side, if this was a glass side or something, you could see kind of the water level here is about this high, so you have another like a little trough that's similar to this big trough. It's kind of like the cone situation. So we're looking for the HCT, how high this is, how fast this water level is rising. When H equals 5 again. Kind of like my last example. Sorry about that. Okay. So we're going to use similar triangles again to get a relationship, but first of all, let's write the volume. So the volume would be just base area. Volume of a prism is just base area, in which case it's going to be a triangle, and then we're going to call this, instead of calling it height, we'll call it length from L. So now we can use our formula because our this base area, if we set this up, tilted up on this, set it on the triangular side, be a triangular prism. So the base area is a triangle, so the formula for the area of a triangle, remember like before when a circle is pi r squared, now it's a triangle, so that's going to be 1/2 base times height. And times the length, and in this case the length is going to be 22, so I can just put the 22 down there. And that's going to simplify a little bit nicely, a little bit easy to be 1/2 of 22 is 11, so I can just say 11 times base times height of the bases here of the triangle. Okay, because this is staying the same. This isn't changing. These are changing here, H and B. So we want to take the derivative, but again we got the same situation where we've got 2 unknowns, so we have to reduce this to 1 unknown, kind of using the fact that these are similar triangles as our constraint. So now remember, this water level is rising, so this is always going to be parallel to the top here. So these lines are parallel. That means these angles are congruent by corresponding angles of parallel lines cut by a transversal, and then these angles are also congruent by being corresponding angles of this transversal cut by these 2 parallel lines. One is the water level and one is the top of the trough because it's squared off. Okay? So that means these triangles are similar, which means also that the heights are similar. Not only are the, these little bases are similar, but or proportional, I should say proportional, because you can look at these triangles and say these are proportional. Either way, any linear components would have the same ratios. So if the ratio of the base to the height of this big triangle is 14 to 6, then the ratio of the altitudes would be the same and the ratio of the perimeters would be all the same. So we can say big triangle to small triangle and big height to small height. Or the same. So base to base. So my big triangle, the base is 14, and the small triangle here, this base I call that B. So big triangle to small triangle, 14 to B, is the same thing as big triangle 6 to little triangle H. And this is the part that's changing. So the H is going up. So even though it's upside down, it works out because it's going up because we're adding water into this. We're pouring water into this thing. Okay. So like I said, this ratio would be, 14 to 6, or 14 to base, 6 to height. It would be the same thing. We'd have the same ratios for the perimeters also. Any linear measurements have the same ratios. So we can accept that. And then we just cross multiply, so we got 14H equals 6 times B. And I did mention this before, I think on some other examples, that you could also, just look at half of these, and then we would have also similar triangles by these being right triangles and by angle, and then you can double everything. You get the same ratio. So it's a little bit more work. This is a little bit more straightforward. And we want to find dHdt, so we want to eliminate the B, so we'll solve for B. So that's going to be 14 over 6H equals B. I can reduce that to be 7 over 3. 2 goes into 14. 7 over 3 H equals B. And then I can write this volume equals 11. And instead of writing B, I can write 7H over 3. And then times this H. And then we can just multiply, so we get volume equals 77 over 3 H squared. And now we're ready to take the derivative. So dV dt equals 77 over 3 times 2H times dH dt. Don't forget the chain rule. This is what we're trying to solve for. Now we just substitute our data in, and dV dt was 3, so this is 3. And that equals, and this doesn't, there's not much simplifying I'm going to be able to do, so 2 times 77, that's 14, 154. And my H was going to be 5. And there's my dHdt. And none of these numbers, these don't work out as really nicely as the previous problem I did. So multiply both sides by 3 and divide both sides by this. So we've got 3 times 3 is 9, so we got 9 divided by 5 times 154. 5 times 4 is 20. Carry it to 5 times 5 is 25, 27. Carry it to 5, 6, 7. And that's going to be in feet per minute, because it's linear. And that's going to equal dH dt. Okay? So not so nice mathematically. Okay? So try to remember again that these triangles are similar. So not only is the ratio of their corresponding sides the same, the ratio of their corresponding perimeters would be the same, and the ratio of their corresponding altitudes would be the same. So big base to small base, big altitude to small altitude. Those are the same for those similar triangles. Okay? So I hope I multiplied correctly. 20 carrier 2, 27 carrier 2, 7. Looks okay. Always double check your arithmetic.